Welcome to another deep dive with us today. We're going to unpack something you experience every single day but probably don't think too much about, the chemistry of sunlight.
Oh, that's a good one.
Yeah, imagine this, right? You're at a cocktail party and someone asks, what's so special about sunlight anyway?
Right.
And you, armed with some cool chemical knowledge, drop 5 mind-blowing factoids about sunlight. You'll be the hit of the party. We're going to explore the hidden chemistry of sunlight.
Yeah.
From, like, tiny powerhouses called photons to the miracle of photosynthesis, and even how we can capture the sun's energy for our own use.
Yeah, that's going to be interesting.
By the end of this, you'll see sunlight in a whole new light.
Uh-huh.
Pun intended, of course.
Okay, so most people just see sunlight as, well, light.
Right.
There's a lot more to it than meets the eye, though.
Right. It's like that classic prism experiment.
Yeah.
From science class splitting light into a rainbow. That's our starting point for understanding what sunlight is really made of.
Exactly. What we see as that beautiful rainbow is actually a spectrum of different types of light, each with its own energy level. We've got ultraviolet or UV, visible light, and infrared.
Okay.
You know how we feel the warmth of the sun?
Yeah.
That's infrared radiation at work.
So it's not just like one type of light.
No.
It's a mixture of different kinds.
It is a mixture, precisely. And this mixture is incredibly important. It influences how sunlight interacts with everything on Earth, from our bodies to plants and even the atmosphere.
Okay, that's point one for our cocktail party knowledge arsenal. Let's zoom in even further now to something even smaller. Photons and other tiny particles of light. What makes them so special?
Well, photons are like little packets of energy that travel at, well, the speed of light. I like to think of them as like tiny bullets of light, each carrying a specific amount of energy.
Oh, okay, so how does that then explain why we see different colors? Is it because different colored photons have different energy levels?
You got it. You got it. Blue photons are more energetic than red photons, for example.
Okay.
And our eyes have evolved to detect those differences in energy as different colors. It's how we perceive the world around us.
Wow, so the color we see is literally a measure of the energy carried by these tiny photons. That's just incredible. It's like a secret code embedded in the light itself.
It really is. And this concept of photon energy is crucial for understanding so many things, from how plants capture sunlight for energy through photosynthesis to how solar panels work.
Speaking of photosynthesis, that's our next cocktail party gem. It's the perfect example of how sunlight, or more specifically, photons, can be harnessed to power life itself.
Absolutely. Photosynthesis is the foundation of most life on Earth. Think about it. A plant soaking up the sun's rays. It's literally using that energy to grow and thrive. It's nature's solar panel.
Yeah, and that's all thanks to chlorophyll, right? The thing that makes plants green.
Chlorophyll is the key. It's a pigment that can capture the energy from photons, especially red and blue ones.
Okay.
And then the plant uses this captured energy to convert carbon dioxide and water into sugars. It's like they're eating sunlight.
And those sugars are their food source.
Yes.
But it's more than just plants eating sunlight. It's the basis of the entire food chain, isn't it?
Exactly. Photosynthesis is the starting point for most of the food we eat and the oxygen we breathe. It's hard to overstate just how fundamental this process is for life on Earth.
Okay, that's 3 incredible factoids down. We're on a roll. But sunlight isn't all sunshine and roses, is it? We can't forget about UV radiation.
Ah, yes, UV radiation. It's a double-edged sword. We've all experienced the downside. Sunburn. That happens when those high-energy UV photons damage our skin cells.
Ouch, yeah. I've been there.
Yeah.
But I've also heard that UV radiation is essential for producing vitamin D. So it can't be all bad.
Right.
What's the deal with that?
That's the fascinating part. The same UV radiation that causes sunburns also triggers our bodies to produce vitamin D, which is crucial for bone health. So it's about finding that balance.
Right.
Enjoy the sun, but protect yourself from overexposure.
Makes sense. Moderation is key. Okay, for our final cocktail party-worthy factoid, let's talk about something I find really exciting. Solar energy.
Okay.
Harnessing the power of the sun to power our world.
Now we're getting into the realm of applied science.
Yeah.
We've talked about how plants use sunlight for energy, but humans are getting pretty good at it too, thanks to technologies like solar panels.
Yeah, solar panels are popping up everywhere these days, but how do they actually work? I mean, they're just sitting there soaking up the sun. Is it really as simple as it looks?
It might seem simple, but the science behind it is fascinating. Solar panels are made of materials that can absorb photons and release electrons. These electrons then flow through a circuit, creating an electrical current.
So it's literally turning sunlight into electricity.
Exactly. And there are also solar thermal systems that use sunlight to heat water, which can be used for all sorts of things. Both technologies offer clean and renewable alternatives to fossil fuels.
Okay, that's amazing. We've covered a lot of ground here, from the basic chemistry of sunlight to those tiny powerhouse photons, the magic of photosynthesis, the 2 sides of UV radiation, and finally, harnessing the sun's energy for our own use. I feel like I'm ready to ace any science trivia night now.
You're definitely well equipped. But you know what's really fascinating? We often think about the direct impact of sunlight, like warmth, light, and sunburn.
Right.
But what about its role in broader environmental issues, like take smog, for example? Sunlight actually plays a key role in its formation.
Oh, that's interesting. I always thought smog was just caused by, like, pollution from cars and factories. How does sunlight fit into that picture?
Well, smog formation is actually a photochemical process.
Photochemical.
Photo, meaning light. Sunlight provides the energy to trigger chemical reactions between pollutants in the air.
So those pollutants from cars and factories are already in the air, and then sunlight comes along and it kind of sets off a chain reaction that creates smog.
Exactly. The energy from UV radiation and sunlight breaks down those pollutants, leading to a cascade of reactions that produce ground-level ozone, a major component of smog.
Okay, that's fascinating and a bit concerning too. So how do we tackle this problem? I mean, we can't exactly like control the sun, can we?
You're right, we can't control the sun, but we can control the pollutants we release into the atmosphere.
Right.
And we've developed technology to do just that, like catalytic converters in cars.
Right, those help reduce emissions from vehicles. How do they work though? Do they somehow like block sunlight from interacting with those pollutants?
Not quite. Catalytic converters don't block sunlight, but they use a catalyst, often a combination of metals, to convert those harmful pollutants and exhaust gases into less harmful substances before they're even released into the air.
So it's like a mini chemistry lab inside your car cleaning up the exhaust before it has a chance to react with sunlight and create smog.
That's a great way to think about it. It's an example of how we can apply our understanding of chemistry to create solutions for environmental problems.
Yeah, this has been a really eye-opening conversation. I never realized how much chemistry was involved in something as seemingly simple as sunlight.
It's everywhere. And the more we understand these chemical processes, the better equipped we are to appreciate the wonders of our world and address the challenges we face.
Speaking of wonders, you mentioned earlier that understanding photon energy is crucial for grasping how solar panels work. Can we dive into that a bit more? I find the idea of capturing sunlight for energy absolutely fascinating.
Absolutely. It's one of the most promising areas of scientific research today. At its core, a solar panel is essentially converting light energy into electrical energy. And it does this by taking advantage of something called the photovoltaic effect.
Okay, break that down for me. What is the photovoltaic effect?
Essentially, when a photon, that little packet of light energy we discussed earlier, strikes certain materials like silicon, it can knock an electron loose. This creates a flow of electrons, which is what we know as electricity.
So solar panels are designed to capture those freed electrons and channel them into a usable current.
Precisely. They're carefully engineered with the layers of these special materials, creating an electric field that directs the flow of electrons. It's like a one-way street for electrons, all powered by sunlight.
That is so cool. So are there different types of solar panels, or do they all basically use the same principle?
There are a few different types, but they mostly rely on the same fundamental principle of the photovoltaic effect. Some variations focus on using different materials or designs to improve efficiency or cost effectiveness.
Got it. And what about solar thermal systems, the ones that use sunlight to heat water? How do those work? Is it the same basic principle?
Solar thermal systems are a bit different. They don't generate electricity directly. Instead, they use sunlight to heat a fluid, usually water or a glycol solution,
Okay.
which can then be used for heating buildings, providing hot water, or even generating electricity through steam turbines.
Okay, so instead of freeing electrons to create a current, solar thermal is all about capturing that heat energy.
Exactly, and both solar photovoltaic and solar thermal technologies have the potential to play a huge role in transitioning us towards a more sustainable energy future.
It's exciting to think about a future where we can harness the power of the sun to meet our energy needs in a clean and sustainable way. It's like we're finally catching up to what plants have been doing for millions of years.
Well said. We've learned a lot from observing nature's ingenious solutions.
That brings us back to photosynthesis. We talked about its importance for life on Earth, but I'm curious, are scientists trying to replicate that process artificially? I mean, could we create our own artificial photosynthesis to produce energy?
That's a great question, and the answer is yes, absolutely. Researchers around the world are working on mimicking the process of photosynthesis to create artificial systems that can convert sunlight into chemical energy, much like plants do.
Wow, that's mind-blowing. So how does that work? Are they creating like artificial leaves or something?
It's not quite as simple as creating artificial leaves, although that is one avenue of research. But essentially, they're trying to develop systems that can capture sunlight, split water molecules, and use the resulting hydrogen to create fuels like hydrogen gas or even liquid fuels.
So instead of generating electricity directly, like solar panels, Artificial photosynthesis aims to create fuels that we can store and use on demand.
Exactly, and that's one of the major advantages of this approach. Storing solar energy in the form of chemical fuels could help overcome the intermittency challenges associated with solar power, making it a more reliable and versatile energy source.
It all sounds incredibly complex. Are there any major breakthroughs on the horizon?
There are some very promising developments. For example, researchers have created artificial systems that can split water using sunlight with remarkable efficiency. But there are still many challenges to overcome before artificial photosynthesis becomes a commercially viable technology.
It's exciting to think about the possibilities, though. I mean, if we could truly crack the code of artificial photosynthesis, it could revolutionize the way we produce and consume energy.
Absolutely. It's a field with immense potential, and it highlights the incredible power of harnessing the sun's energy for a cleaner and more sustainable future.
This entire deep dive has been truly fascinating. From the hidden chemistry of sunlight to the incredible potential of solar energy and the mind-boggling research into artificial photosynthesis, I feel like I've gained a whole new appreciation for that big, bright star in the sky.
Me too. It's a reminder that even the most familiar things, like sunlight, can hold incredible secrets and possibilities waiting to be uncovered.
You know, it's amazing to think about how far we've come in understanding and harnessing the power of sunlight. But I can't help but wonder about, like, those early scientists who were just starting to unravel the mysteries of the sun. Like, what were their theories like?
Oh, those early theories? They
Yeah.
could be quite imaginative. Some ancient cultures believed the sun was a god riding across the sky in a chariot. Others thought it was like a giant ball of fire constantly being replenished.
Oh, wow.
It wasn't until the 17th century that scientists began to develop more accurate models based on observation and experimentation.
So when did we finally figure out that the sun is actually a star? Like all those twinkling points of light in the night sky.
That realization came about gradually, with contributions from many brilliant minds.
Okay.
In the 16th century, Nicholas Copernicus proposed his heliocentric model of the solar system, placing the sun at the center.
Right.
Then in the 17th century, astronomers like Galilei used telescopes to observe the sun in greater detail, further supporting the idea that it was, in fact, a star.
That must have been a truly revolutionary concept at the time, shifting our entire understanding of the universe and our place within it.
It was a paradigm shift, and it paved the way for further discoveries about the nature of stars and their energy.
Okay?
In the 19th century, physicists began to understand the concept of energy conservation and realized that the sun must be powered by some internal source of energy.
And eventually that led to the discovery of nuclear fusion as the engine driving the sun's energy output.
Exactly. In the early 20th century, physicists developed the theory of nuclear fusion, which explained how the sun could produce such vast amounts of energy by fusing hydrogen atoms into helium in its core.
Wow.
This was a truly groundbreaking discovery that revolutionized our understanding of stars and their life cycles.
It's mind-boggling to think about those nuclear reactions happening millions of miles away, providing the light and warmth that sustain life on Earth. Makes you realize just how interconnected we are with the cosmos.
It really does, and it underscores the importance of continued scientific exploration and discovery. Who knows what other incredible secrets the universe holds waiting to be unveiled by future generations of scientists.
That's what makes science so exciting. It's a never-ending journey of exploration and discovery, constantly pushing the boundaries of our knowledge and understanding. Well, on that note, I think it's time to wrap up our deep dive into the chemistry of sunlight.
It's been a fascinating journey exploring the hidden chemistry of sunlight, from those tiny powerhouse photons to the miracle of photosynthesis and the incredible potential of solar energy.
And we even touched upon the early theories about the sun and the groundbreaking discovery of nuclear fusion as its energy source.
It's a reminder that even something as familiar as sunlight holds incredible secrets and possibilities just waiting to be uncovered.
So the next time you feel the warmth of the sun on your skin, remember all the amazing chemistry and physics happening behind the scenes.
And who knows, maybe you'll be inspired to share some of those mind-blowing factoids at your next cocktail party.
Thanks for joining us on this illuminating deep dive into the chemistry of sunlight. Until next time, keep looking up and keep those brains buzzing.